our previous lesson, we saw that the differential equation that describes basically a sagging beam, sagging under its own weight, is E times I, fourth derivative of y with respect to x, equals W of x, where W of x is the weight per unit length of the beam. And now we're going to solve the differential equation. And what we'll find is the deflection curve. That is, equation whose graph is actually a picture of the beam. Our beam is of length L, and W naught is a constant, and we're told that W of x, the weight per unit length, is W naught. So a constant on the right-hand side. X is between 0 and L. In this particular problem, our beam is simply supported at both ends. And you may remember we looked at boundary conditions for beams that are either free at one end, embedded at one end, or simply supported at one end. The boundary condition for simply supported is y of 0 and y double prime is 0. The beam is simply supported at the left end when x is equal to 0. So we have that y of 0 is equal to 0, and what was it? Y double prime of 0 is equal to 0. We're also told that it's simply supported on the right end at x equals L. And the way we use that information is y of L is equal to 0 and y double prime of L is equal to 0. Notice we have information about different values for the independent variable, making this a boundary value problem. If we were simply supported at one end and embedded at the other end, pick one of them to be a 0, one of them to be L, and then grab the appropriate boundary conditions to proceed with solving the differential equation. I've got good news. The differential equation we're solving is actually y, well, the fourth derivative of y is equal to W naught over EI, a constant. So the third derivative of y is equal to W naught over EI x plus constant integration. For the second derivative, we just anti-differentiate that thing, and we end up with W naught over 2EI x squared plus, I relabeled the constant c as C1 because I realized we needed a few to keep track of. Anyway, y double prime equals W naught over 2EI x squared plus C1x plus C2. Y prime is of course going to be W sub 0 over 6EI x cubed plus 1/2 C1x squared plus C2x plus C3. And then finally y is W naught over 24EI x to the fourth plus 1/6 C1x cubed plus 1/2 C2x squared plus C3x plus C4. Okay, great. Y of 0 equals 0. Putting in 0 in place of x gives us directly that C4 is equal to 0. Y double prime of 0 equals 0, as you can see, is going to give us that C2 is 0. That simplifies y double prime to W sub 0 over 2EI x squared plus C1x. And that's useful because y double prime of L is equal to 0. Thus, putting L in place of x is going to give us 0 equals W naught over 2EI L squared plus C1L, giving us C1 equals W naught over 2EIL. And then I will leave it to you to use the boundary condition y of L equals 0 and the equation y with the information that we have gives us that C3 is equal to W naught over 24EI times L cubed. Putting all this together gives us that y of x is equal to, I'm going to factor out so that things are nice, W naught over 24EI times x to the fourth minus 2LX cubed plus L cubed x, a fourth degree polynomial in x. That's our deflection curve. Next, we're going to use a graphing utility to graph the deflection curve. How nice is this? W naught is 24EI and L is equal to 1. So then with that, y of x turns out to be simply x to the fourth minus 2x cubed plus x. But remember, at the beginning of this conversation, we assumed that down was going to be positive. So what we actually are going to graph is the negative of what I just said. And remember that our solution is only good for x between 0 and L. I've used Desmos as my graphing utility. You can see here our solution and then the interval from 0 to 1. And this is a picture of the beam. This curve here is what the beam would look like under these circumstances.